Hello and welcome to this new video. In today's video, we will study about the congruences, which is very important concept in the field of number theory. Let's start with the definition of congruence. Let M be a fixed integer we say that A is congruent to B modulo M if M divides the difference of AB, means A minus B. Alright. And we write A is congruent to B mod M. The integer M is called modular. For example, if we fix M to be 6, then A, for example, we take 11 and B is 23, then clearly this 6 divides 11 minus 23. This means 11 is congruent to 23 or 23 is congruent to 11 mod 6. And similarly, if we take A to be 11 and B to be 17, then also 11 is congruent to 17 mod 6. Alright. Now we move to some remarks. First remark is, if M divides A, this means there must exist an integer t such that A is equal to M into t. Also we can write it minus M into minus t, and this implies that minus M also divides A. Thus we restrict ourselves to positive modulars. Next remark is, if A is congruent to B mod M, then, or we can say A is congruent to B mod M if and only if A and B leaves the same remainder when divided by M. As in our previous example, if we see, when we divide 11 by 6, the remainder is 5, and when we divide 23 by 6, the remainder is 5. Similarly, when we divide 17 by 6, the remainder is 5. So all give the same remainder. That's why they are congruent to each other modulo 6. Alright. The next remark is, if m is equal to 0, then A is congruent to B, mod m implies that A is equal to B. Alright, we move to the next remark. For each integers A and B, A is congruent to B always, mod 1. Means any two integers are congruent to each other, mod 1. Alright. Now we move to theorem. The statement of theorem is, let A, B, C and D be integers, then and m is fixed integer, then we can prove that A is congruent to A mod m. Second is, if A is congruent to B mod m, then B is congruent to A mod m. And third is, if A is congruent to B mod m and B is congruent to C mod m, then A is congruent to C mod m. Alright. The fourth is, if A is congruent to B mod m and C is congruent to D mod m, then A plus minus C is congruent to B plus minus D mod m. Alright, there are some other properties as well, but first we will prove these four properties. Proof. The proof of first is very simple, because A minus A is equal to 0 and 0 is divisible to every integer, therefore m divides A minus A, and this means A is congruent to A mod m, as by definition of congruence. The second is, if it is given that A is congruent to B mod m, this means m divides A minus B. And since we know that A minus B is equal to minus time B minus A, or we can say that B minus A is equal to minus time A minus B. So this means m also divides minus time A minus B, which is B minus A, and this means B is congruent to A mod m. Now the third property is, if A is congruent to B mod m and B is congruent to C mod m, then A is congruent to C mod m. Because it is given that A is congruent to B mod m, this means m divides A minus B. Also it is given that B is congruent to C mod m divides B minus C, and if m is dividing A minus B, m is dividing B minus C, then m divides their sum as well. This means m divides A minus B plus b minus c. And if we see that minus b and b can be cancelled with each other, and this implies that m divides a minus c, and this means a is congruent to c mod m. Alright. Now the fourth property, the proof of fourth property is that it is given that a is congruent to b and c is congruent to d. So m divides a minus b and m divides c minus d. Then m divides their sum as well as their difference. Then m divides a minus b plus minus c minus d, and that is actually equal to m divides a plus minus c minus b plus minus d, and this gives us the required result. Alright. Some other properties are, the statement of property are, if a is congruent to b, if a is congruent to b mod m, then AC is congruent to BC mod m. The proof of this property is, we can see that A is congruent to B mod m. This means m divides A minus B. And if m is dividing A minus B, then m will divide any multiple of A minus B. This means m divides C times A minus B. And this means m divides AC minus BC. This means AC is congruent to BC mod m. Alright. The sixth property is, if A is congruent to B mod m, then A to raise power k is congruent to B to raise power k mod m for all k greater or equal to 1. But if ak is congruent to bk mod m for k greater or equal to 2, then it is not true every time that A is congruent to B mod m. May not be true. So there are two parts of this proof. First, we have to prove the identity that whenever A is congruent to B mod m, then A to raise power k is congruent to B to raise power k mod m. At the same time, we have to show that if ak is congruent to B to raise power k mod m, this does not imply that A is congruent to B mod m. Alright, we start the proof. Since it is given that A is congruent to B mod m, this means m divides A minus B. And then we know that A to raise power k minus B to raise power k can be written as A minus B into A to raise power k minus 1 plus A to raise power k minus 2b plus so on up to B to raise power k minus 1. So it is clear that this ak minus bk is multiple of A minus B. And since m dividing A minus B, then m will divide any multiple of A minus B. So this means m divides ak minus b k, and this means that ak is congruent to bk mod m. To disprove anything, we just need one example. If we take a is equal to 4 and b is equal to 8 and m is equal to 3, then a square is congruent to b square mod 3, because a square means 4 square is equal to 16, and this gives 1 as a remainder when divided by 3, and similarly 8 square is 64, which also gives the remainder 1 when it is divided by 3. Therefore a square is congruent to b square mod 3, but a is not congruent to b mod 3. So it means that we have proved that ak is congruent to bk mod m does not imply that a is congruent to b mod m. That's all about this video. See you next time.